Let's take a look at another kind of compound interest formula. Here I've drawn a diagram where let's say that you are putting money into a bank. But in reality, you can always take your money out at any point in time. I can take my money out at 2 months. I can even put money in at 6 months. There's nothing to stop me from taking money out or putting money in. So let's say I put money into a bank at 3:02 p.m. and then I put money in again at 3:05 p.m. I need to be able to have a way to still accumulate compound interest based on any moment in time, which is why if the bank only paid me 2 times a year, semi-annual, that wouldn't really make a whole lot of sense. Even if they paid me 4 times a year, it still doesn't make a whole lot of sense. I need to be able to get paid at any moment in time. So 2, 4, even 6 months, even 12 times a year, these are too limiting. Even 365 days a year, still too limiting, because I could be depositing money multiple times on the same day. So I need to be able to continuously be able to earn money. And that's actually how banks work. You are basically compounding your money 100 times a day or 100 times a year, 400 times a year, 1,000,000 times a year. You need to compound it indefinitely. Okay? So how do we exactly see that through a formula? Well, recall our compound interest formula is made up of P, the principal, times 100% of your money plus the rate over the number of compounds to the NT power. Again, number of compounds and how many years you're actually putting your money in. Okay? Now, as we look at this formula, we need to consider as that value of compounds, the N value is getting more and more large, where basically it's going to infinity. So we're taking the limit as N goes to infinity. So what exactly does this do to our formula? Well, what we're going to end up doing is trying to rewrite this formula here, okay? If you recall from a previous section, we saw how there was a formula in which we can write 1 plus 1 over n to the n power. If you recall, as that n value got larger and larger, this entire expression turned into the value of e. If we actually plug e into the calculator, we end up getting that value of 2.7182 and then ... right? It was an irrational number. So we saw that this expression, as n got infinitely large, it basically gave you the value of e. So what we're going to do is actually try to incorporate this formula into our compound interest formula. Notice in this formula, we do have a 1 on the numerator. So that's going to be our goal, trying to set up a 1. As we look at our equation here, I notice that there's an r as the numerator. So what I want to do is change this. So I'm going to say 1 plus 1 over. Now how am I going to make that 1 over something? Well, hopefully as a fraction, what you see is that technically 1 over n over r would give me the same result as r over n. Those are basically equivalent fractions, right? So I'm going to write that as n over r to the nt power. Well, keep in mind that what I want this to look like is like a 1 plus 1 over x. So technically, what I'm trying to get you to see here is that n over r is really equivalent to a value of x. So if I were to rewrite this just a little bit, I multiply both sides by r, I can see that n is equivalent to x times r. Well, I do see that there's an n in my exponent, so since I'm trying to convert everything in terms of x's, I'm now going to rewrite that n as an xr, like that. And then don't forget that we still have a t power to the side of that. And don't forget we also need to multiply that by our principal. Okay, so now as we have changed our variables, now we're seeing as x goes to infinity, let me rewrite this, limit as x goes to infinity of p times 1 plus 1 over x to the x, and I'm just going to separate my powers just a little bit, times RT. what you'll see is that the limit as x goes to infinity of 1 plus 1 over x to the x, this is exactly what we have found earlier, right? This is the value of e. And so now what we have is a new formula. We have the principal amount times e, and then we still have it to the RT power. This is going to be our new formula for being able to compound our money continuously. Because if you recall, E is basically saying that we are always getting paid. We're getting paid infinitely number of times. So you're getting paid by the millisecond, by the nanosecond. You're always accumulating money. And so this is where banks actually use this formula, PE to the RT. So as we take a look now at our notes over here, okay, I'm looking still at 5.7. Going to the compound continuously section, we now have a new formula for compounding continuously, which is PE to the RT power. Okay. All right, going on to the next slide. One other formula I want to bring to your attention is the effective rate of interest. Basically, what this means is that because you're getting paid continuously or in different compounds, let's say that a bank pays you 3% for 1 year. Well, by the power of compounds, remember what we're doing is we're taking the 3%, but breaking it down based on the number of compounds. Let's say we're getting paid quarterly. Then you're taking the 3% and breaking it into fours. So essentially you're compounding each of those fours upon one another. So 3% actually turns into something a little bit more. Maybe you're actually getting paid 3.09%. You're getting paid a little bit more than the true 3% that got broken up. That's basically what we call the effective rate of interest. The effective rate of interest. Another word for that maybe you've heard of on the radio might be like APY or APR, things like that. Those terms that they give you is basically telling you the annual percentage yield. It's basically saying what is the equivalent form of that percentage. Okay, so you're getting paid a little bit more. So here's how you calculate it. Based on our formula, compounding n times per year, the effective rate of interest is given by 1 plus r over n to the n power. That's basically what you see in the compound interest formula. But what you want to do is take away 100% of what you had put in, so minus 1. What you'll end up with is just purely the profits. Okay, so for compounding continuously, because that 1 plus r over n to the n power is basically the same thing as e to the r, there it is. There's your total amount, but take away your actual amount you put in, and you'll just get purely the profits. Okay, so let's take a look at example 6, just to clearly see what's going on. Find the effective rate of interest. So since we're finding the effective rate for 5% compounded quarterly, what we want to find out is how much will you earn after, or let's say in 1 year. Okay, how much will you earn in 1 year? So we just take our formula, 1 plus our rate of interest is 0.05 broken up into 4 equal installments, and we take it to the 4th power, getting paid 4 times per year. And this is only for 1 year, so we take it to the 1st power. Okay, so that amount, let's calculate that. Clear. So we have, in parentheses, 1 plus, it was 5%, I believe, for 4 times. And then that is taken to the 4th power. And then you can even add a 1 in there if you want. So times 1. Oops, wrong spot. It'd be 4 times 1 like that. Nope, didn't work there. Parentheses. There, it would look like that. Of course, that doesn't change anything. But we get 1.0509. Okay, let's go ahead and write that down. So this is an amount of 1.0509. Don't forget what we want to do now is subtract 1, so minus 1. and that's going to give you 0.0509, telling you that your APY, your effective rate, is going to be 5.09% total interest. Okay, as you can see, 5% is not the true amount you got paid. You actually got paid 5.09%. So you'll always see that the APY is always going to be greater than the actual interest rate. Always. Okay? So that's how you can find the effective rate.